Let me ask you a quick question. If you have a piece of paper in front of you, or you can do this in your head, could you draw me an alpha particle? What is an alpha particle? Well, an alpha particle contains two protons and two neutrons. And it doesn't have any electrons in orbit around it. So because it has two neutrons and no electrons, what does this say about the charge of an alpha particle? Well, protons have a charge of positive E, and E is 1.60 times 10 to the minus 19 coulombs. So the charge of an alpha particle is equal to positive 2e. But you might have already noticed that this alpha particle here looks very similar to the nucleus of a helium atom, minus the electrons. And we can write this alpha particle like this. So we have the element of helium with a charge of positive 2e. And we came across this symbol notation in a previous lesson, and it looks a bit like this. So we've got X for our element, and we've got an A at the top here and a Z at the bottom. Can you remember what the A and Z represent? And for our alpha particle here, the A is equal to 4 and the Z is equal to 2. Well, the Z is the proton number, and it's sometimes called the atomic number, and A is the nucleon number, which is sometimes called the mass number. So the nucleon number represents the total number of protons and neutrons in the nucleus, and the proton number gives us the number of protons. So what do you think is the source of these alpha particles? So let's say we have a very large nucleus with a large number of protons and a large number of neutrons. And you'll find these types of elements fairly low down on the periodic table. So uranium would be an example. But when we have a lot of protons in a confined space, very close together, because protons have a positive charge, or the same charge, there is an electrostatic repulsion between all the protons within the nucleus. So they're all trying to push each other apart. Now the neutrons have zero charge. So what holds the nucleus together and keeps it stable? Well, it's something called the strong nuclear force. We won't cover this in this lesson, but this force is able to hold the protons and neutrons together in the nucleus and overcome the repulsive force, the electrostatic repulsive force from the protons. But the more protons we pack into a nucleus, the harder it is for this strong nuclear force to hold everything together. So what happens with heavy nuclei is that to become more stable, they tend to spit out a helium nuclei, something like this. And in doing so, they can get rid of 2 extra protons. And with less protons in the nucleus, there's less electrostatic repulsion between these protons, and the strong nuclear force can do a better job at holding the nucleus together. And when a heavy nucleus spits out an alpha particle, this is called alpha decay. So let's look at an example nuclear equation that undergoes alpha decay. So we're going to have a look at uranium-234. And the 234 here represents the nucleon or mass number of the uranium here. In other words, it's the total number of protons and neutrons in the nucleus. It gives no indication at the moment on the number of protons we have in uranium, but all uranium elements contain 92 protons. It's the proton number that makes up the element. So the symbol for uranium is U, and for the proton number, we've got 92. And if I go back to the periodic table, we can see uranium here has a value of 92 on the left-hand side. That is the proton number, the number of protons in the nucleus. So our uranium has a total mass of 234. 234. Now this undergoes alpha decay, producing some element X, and we'll find out what this element is in a minute. And it spits out a helium nucleus with a positive charge. And the helium nucleus has a mass number or nucleon number of 4 and a proton number of 2. And this process also releases energy in the form of the kinetic energy of the helium nuclei being ejected from the heavy nucleus, and the daughter nuclei or nuclide also having kinetic energy. And there'll also be some gamma radiation emitted as well, which we'll get into in a future lesson. But to complete this nuclear equation here, we need to figure out what element our daughter nuclide is and what the nucleon number and the proton number is. So how can we work this out with all the information we've got here? Well, the uranium element here, which is also called the parent nuclide, so I'll write this down. The parent nuclide must lose 2 protons from the nucleus because it's ejecting a helium nuclei here. So what does this mean in terms of the proton number here? Well, it simply reduces by 2. So with this daughter nucleus here, its proton number will be 90. What about the nucleon number for this new element here? Well, the uranium nucleus also loses a mass of 4. So this number here reduces by 4, which gives us 230. So with this information here, if we look on our periodic table, can we work out what element this is? It's got a proton number of 90. What element on this periodic table here has a proton number of 90? Well, if we have a look at the uranium here with a proton number of 92, we go back one, we've got a proton number of 91, so it can't be this element here. But we got the element of thorium, which has a proton number of 90. So our new element must be thorium. So we can change this to thorium. So when this alpha particle is ejected from the heavy nucleus here, the uranium nucleus, it has some kinetic energy. This means it has a velocity. And these alpha particles can be ejected at a velocity of about 5% of the speed of light, which is about 10 to the 7 meters per second. But these alpha particles don't travel that far in air. They can only travel about 2 or 3 centimeters in air, which is about an inch. And as they travel through air, they're very efficient at stripping away electrons from other atoms. So these helium nuclei will strip away electrons from oxygen molecules and nitrogen molecules in the air. But to be able to separate electrons from these molecules takes energy. And this causes the helium nuclei to lose energy and therefore to lose its velocity. So very quickly they start decelerating, and that's why they can't travel that far in air. And if you've studied the Rutherford gold foil experiment, where they use alpha particles to estimate the size of the nucleus, they have to do this in a vacuum chamber because these alpha particles cannot travel that far in air. So let's try one more question. Write down the nuclear equation to represent the alpha decay of a thorium nucleus to a radium nucleus. So how can we write this down as a nuclear equation? Well, on the left-hand side, we can write our element with a proton number of 90, and this element has a nucleon number or mass number of 232. And we already know what the daughter nuclide is going to be. It's going to be radium. So we can write that down, and it spits out an alpha particle at 4 and 2. So our goal is, without looking at the periodic table, is to work out what the proton number is and the nucleon number is for this radium nucleus here. So because thorium loses a helium nuclei, it gets transmuted into this radium nucleus here. It loses 2 protons from the nucleus. So that gets reduced to 88. The nucleon number loses 4 particles from the nucleus. So 232 minus 4 becomes 228. And that's our completed nuclear equation.